So, hello everyone. My name is Mouadh Khammassi. Today I'm presenting my thesis titled Design of Kinetic Building Envelope of a High-Performing Building Using BIM. My supervisor is Mia and my co-supervisor is Yaka. So if we start about the introduction, about the context of the thesis, now buildings are really are a significant contributor to global energy use and emissions. So that's why architects and engineering are trying to find sustainable alternative solutions. One of the main things is like the role of building envelopes, because the building envelope is like the boundary between exterior and interior, and its like impact is really vital for energy control. And the problem, the limitation in static systems is like they are inflexible to changing environmental condition. That's why kinetic envelopes are a solution really to enhance energy efficiency, and because they adapt to environmental changes. Kinetic envelopes are not only have like a role as a aesthetic function, but also they are energy controllers. So the goal of the thesis is like to develop a design workflow with BIM tools that really demonstrates how this kind of systems can enhance energy efficiency in building design. So we start with the methodology. After reviewing a lot of research, we develop a workflow to design the kinetic facade. So the workflow is basically divided in two main sections. The first part is to develop a base case within Revit plus the kinetic unit and place the kinetic unit on the facade. So all of that it will be done within Revit and Dynamo. And after that, we will integrate that into Grasshopper using Rhino inside Revit to do the responsive system of the kinetic facade. And after that, we will do like a seasonal sensitivity adjustment of the kinetic facade, and we will do the solar radiation analysis also in Grasshopper of the system. After that, we will export the data to analyze and visualize it, and also to do an interactive interior visualization of the kinetic system. So if we start with the base case building design, so we choose to a base case, an office building with really a large glass surfaces. Why we did that? We chose this base case because it's really like a large surface oriented south is really sensitive to climatic factors, and it really has like a huge potential for energy savings. So the main component of the kinetic facade is really the kinetic unit, because if we define the kinetic unit correctly in the beginning, is the main component of the kinetic facade. So first we chose an adaptive component and create the skeleton of the facade, as we see here. This skeleton is like a folding system, and after that we assign parameters to this kinetic unit to define how it will behave how it will behave and how it will respond to environmental condition. The key parameters for the kinetic unit are the panel length and the kinetic open. The kinetic open is like a value that between 0 and 0.5, because it's really like a symmetrical system. And also we define the depth. The depth is like the height of the joints, and it's really controlled by the panel length. And also we added a parameter named kinetic open constraints, because really we don't know how the system will behave if we put more value than the open or less value than the open. And we simplified everything in the end in a parameter named close panel. This one, it will be like a percentage controlling how the panel will be closed. And really it's like we simplify everything to be like a simplifying user input. After that, how we will do this kinetic unit, we need to place it on the facade. We place it using Dynamo. Why we did this? Because if we do it using a mass inside into Revit, we cannot really modify every panel like differently from the others. So why Dynamo? Because Dynamo allows adaptive component to be placed on a mass surface without direct binding. Also modifiable instance parameter for panel configuration, and also we have like a flexible grid layout for kinetic unit that we can change the layout wherever we want. So now after placing the kinetic units on the facade, we have the result here of the kinetic facade placed on the base case. So as we see here, the difference percentage of closing of the panels, and here is like a random tests of the panels like opening. So now it's like the panels are like the position of the panels is really random on the facade. We will develop a system that make these panels respond to environmental condition like exterior environment condition. We did that within Rhino with Grasshopper. So the main idea of the script in Grasshopper, it will what it we like to have like extract the panel normals of every panel, and with the sum vector, we will compare the angle between the sum vector and the panel normal, and the more the angle would be less, the more the closing would be more. So as we see in this part of the script, so here we extracted the panels normals of every we extract the normal of every kinetic unit. So and after that we extracted the sum vector. How we extracted sum vectors? Like using Ladybug components by loading an EPW file. EPW file, it contains the weather data. So we have the sum position of along the year. So we can extract using slider of the month and the day and the hour. We can extract the position of the sun of the vector of the sun. After that, we did like the comparison between these two vectors, and we extracted the incident angle. And after that, we remapped these values on the parameter of the closed panel. As we see here, is like the closed panel is different from different of every kinetic unit. As we see in the picture on the app, with the sun position, like the sun when the sun is moving along the hemisphere, we see that the panels are more becoming more and more closed. So the problem in this system, like sometimes in during like winter and seasons that we need more solar inside the building, it's like also closed. So with this limitation, we solve it by doing within Grasshopper a script with Python. The script is for to adjust the system sensitivity based on seasons. So for the seasons of the winter, we adjusted the sensitivity of the system. And as we see in the pictures below, the sensitivity before the script and after the script, how the kinetic panel is becoming less open. And the last part of the script is like to do an energy performance analysis for the system. So the energy analysis of the solar radiation, we did it using Ladybug components, and we used three main inputs. The three main inputs are the kinetic facade. The kinetic facade is the context, and the curtain wall geometry behind the kinetic facade as a receiving for solar radiation, and the schematics. The schematics is like also link it to Ladybug components and have like the info about the solar radiation along the year. And as we see here, we remapped with colors on the facade the solar radiation and also the values. And as we see also, it's here we can see it in Revit also, how we can see on the facade the color coded legend. And the last part of the script, it will be to export these values as a CSV file or Excel file to do analysis for the system. So to analyze the system, we are going to do like three types of analysis. The first one is like the kinetic facade performance and response. We choose like a peak day in the summer, and we follow the responsive system, how it will react. As we see the pattern of the facade are really following the sun position and really becoming more and more close when the sun is like more direct to the facade. And also, if we see the map, the solar radiation analysis, we see that where is like the facade is more blocking the sun, it's more becoming and more blue. It means that it really reduced the solar heat on the facade. So, and we see in the graph below, the purple one is like the system without kinetic facade, and the pink one is like the system with kinetic facade. We see really how much the kinetic facade is reducing the average of solar radiation along the day. Also, the blue line is indicating how much the percentage of the panel is closing. So the panel closure really peaks aligned with the maximum solar radiation value. So when is the maximum solar radiation value, the panel is closing the maximum. So we conclude with this, like the system behavior really meets the design objectives, and really it reduces the solar radiation, especially during critical periods. The second analysis, it will be comparing the kinetic system to a static system. So we choose the static system that have the same geometry and the same U and V. And as we see, the static system have like high solar radiation, like solar exposure, like the average parts are in the yellow zone. So, and the average value is around 0.15 kilowatt hour per meter square. And we see the kinetic system where really the facade is really, where the sun really is really facing the facade is like more reduced solar radiation, and with the average like 0.091 kilowatt hour per meter square. So we can conclude with this analysis that the static system provides some level of protection, but kinetic facade really offer more effective shading, especially in high exposure area. The last analysis, it will be a seasonal adaptation of kinetic facade to see how the kinetic facade works within in summer and winter. So as we see the panels, we see the panels in summer is more like closed, and the average percentage is more than 50%. And during the winter, is like the panels remain mostly open for more solar gain, and the average panel closure is around 25%. So we can conclude with this, like the system really successfully adapts to seasonal changes. After the analysis, we did like a visualization of facade functionality from interior. In this video, we see this work is done within Unity as a game engine. Like we used the model that we developed in Revit, and we exported the CSV file with the percentage with the close of every panel during the day. And as we see, when we change the hour along the day, we can see the functionality of the system, and also we can see down the map where is the sun, the position of the sun. So really, we can like visualize the interior of the system from this side. This system can be more developed if we can let the occupant inside can decide something, like can decide to, because sometimes some people don't want to have like a lot of a closing panel. Like if we let the person that can control the system from inside and have like a dashboard indicating how the solar radiation, how its behavior impacts the solar radiation. So in the end, in the conclusion, the key findings of this workflow, like BIM for kinetic designs, like BIM-based workflow really enabled an effective design, simulation, analysis, and visualization of kinetic system. Kinetic envelope system really can enhance building energy performance by adapting to environmental parameters. And the combination of BIM tools and interior visualization really provided an immersive real-time experience and helps to understand the system performance. And for future research, we can suggest that if we can, in this research, we studied the solar radiation, we can like study more environmental variable, like incorporate more environmental factors to really refine the system response. Offer an occupant operated system, like let the user manually interact with the kinetic system to further optimize the performance. And the third suggestion is like a real world testing, like test a physical prototype of the kinetic facade to really validate the simulation results and assess real world performance. Thank you.